Hey everyone, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. I'm up to section 5.6 of volume 1, and I've been talking about cardinal numbers. Those are the number of elements of sets, finite or infinite. This is my third lesson in this section, and yesterday I began discussing infinite cardinal numbers. I talked about Aleph Null, which is the smallest infinite cardinal number, or what was called countable infinity. And today I'm going to talk about another type of set that's also countably infinite. Turns out it has the same cardinality as the integers or the counting numbers, rational number. And the set of rational numbers, it turns out, also the set of ordered pairs of integers. You might think those sets have more, bigger cardinality than rationals, but it turns out they have the same cardinality. So anyway, let's begin. So how can we see this? This seems like a pretty surprising result. So suppose we wanted to know the cardinal number of the ordered pairs of integers. Well, one way you can do that is you can represent ordered pairs of integers as just a pair of integers m comma n, where m and n are both integers, positive or negative. You can draw them on a square grid. You can draw them on and in the xy plane, they're just these lattice points in a square grid, points with integer coordinates. And it looks like there's a lot more of those than there are of integers, because it's kind of like the square of the number of integers. I mean, you're not only going in one dimension, you're going in two dimensions. But actually, it might surprise you to know that there's actually the same number. There's the same number of ordered pairs of integers as there are integers, even though it looks like there's a lot more. How can we see that? Well, remember what I said last time, last few times, I think, that you can tell whether or not two sets have the same cardinal number. If it turns out they have the same cardinal number whenever there's a bijection, a one-to-one correspondence from one set to the other. And if we can make a bijection from, say, the natural numbers to the set of ordered pairs of integers, then we would know that they're the same number of them. Well, actually, it turns out it's pretty easy to do that. Consider this square spiral I've drawn on this diagram. So we have this blue square spiral I drew that starts at the origin, starts at the point 0, comma 0. And if you like, you can assign an index 0 or 1. It doesn't really matter how you index it, but let's say you start with a number 1 at the origin, 0, comma 0, and then you move along the spiral. Your next point on the spiral is the point 0, comma 1. That's the point, 1 unit above the origin, and that's going to correspond to the number 2, because that's your second number on this spiral. Then you keep going. The next number is 1, comma 1. We move to the right once we moved up 1. So now we're 1 unit to the right and 1 unit above the origin. That corresponds to number 3, and you can keep going like this. You can keep moving in this spiral as many times as you want. And you can get to any ordered pair of integers in this way. Pretty amazing. It might take you a long time to get there, but whatever your ordered pair of integers is, I think I gave the example in this book of 388, comma minus 169. You'll get to that point eventually. I don't know what the index will be, but you will. There'll be some finite number of steps you take along this square spiral to get there. Yeah, so I think you can see that this set does have the same cardinality as the counting numbers. So it's Aleph Null. So no more than Aleph Null. It might surprise you. And another way we can say this is the cardinality of the integers. I think it's pretty obvious. I didn't say this last time, but the cardinal number of the integers, both positive and negative, is also Aleph Null. That's pretty easy to see. You can do, for instance, you can start at 0, then it can go 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. As long as you can list them all, that's why it's called countably infinite. As long as you could list all the elements of an infinite set, then we say that that set is countable. which means that its cardinality is aleph null. So the cardinality of the integers is aleph null, and therefore the cardinality of the ordered pairs of integers should be aleph null squared, because we have aleph null possibilities for the first number m in our pair, and another aleph null possibilities for the second number. So we're kind of squaring the cardinality. So we can write that as equation, which I wrote on the bottom of the slide. Aleph null squared equals aleph null. If you remember yesterday, I gave two other equations of aleph null. Aleph null plus 1 is aleph null, and 2 aleph null is aleph null. Well, not only that, but aleph null square is aleph null. As a matter of fact, it turns out that aleph null to any power, any finite power, is equal to aleph null. I'm not going to prove that here, but it is true. So that's a pretty surprising result, I'd say. And one consequence of that result, you might wonder what's the cardinal number of the set of rational numbers. Fractions, in other words. Reduced fractions like 3/5, minus 2/7, minus 8/11, whatever. I mean, as long as the numerator and denominator are both integers, and they shouldn't share a common divisor, because then we could reduce it if they did. Well, I think it's pretty easy to see that the cardinality of the rational numbers is also aleph null. Because really, when we're doing the rational numbers, you can represent every rational number as an ordered pair. Just the first number, ordered pair of integers. The first number is the numerator, the second number is the denominator. You're not going to get all of them this way. I mean, some ordered pairs we have to exclude. We have to exclude the ones where the denominator is 0, because you can never divide by 0. And you also should exclude the ones where you have a common divisor, or where the denominator is negative. The denominator never has to be negative. You can always make it positive. And whenever you have a common divisor, you can just eliminate it. But that gives you a subset. So you can see that the rational numbers is bijectively equivalent to a subset of the set of ordered pairs of integers. And since it's a subset, we know that its cardinality is less than or equal to aleph null. Well, it also has to be greater than or equal to aleph null, because the rational numbers includes the counting numbers, 1, 2, 3, 4, 5, and we know that those have cardinality aleph null. So we've kind of, we've bound it between two numbers that are the same, aleph null and aleph null. Therefore, we know that the cardinal number of the rational numbers is also aleph null. That's another pretty surprising result. There's the same number of rational numbers, same number of fractions, as you like, as there are integers. And obviously, it looks like there's a lot more rational numbers than integers. As a matter of fact, the rational numbers are what are called dense in the real numbers, meaning that no matter how small an interval, a subinterval you take of the real numbers, you're always going to get a rational number in that interval. As a matter of fact, if you're always going to get infinitely many. So there's a lot of rational numbers, but it turns out that there's only the same number of rational numbers as there are of integers. Pretty counterintuitive result, I'd say. Anyway, that completes my video for today on the cardinality of ordered pairs of integers and rational numbers. Thank you for watching. Long live math, and I'll see you guys next time. Bye.